Good morning. So I will talk about the optimization of the SOL control system. SOL is the upgrade of the FLAO system of LBT. There are 4 copies of the system, 2 that work with Lucy, and 2 inside the LBTI system. The SOL upgrade consists in the change of the detector of the wavefront sensor from a CCD39 to an OCAM2K, a change in the maximum number of subaperture, and then some update of the electronics and of the software to allow a frame rate, an higher frame rate from 1 kHz to 2 kHz. And even the ability to manage a large number of slopes. SOL, like FLAO, works on a wide range of guide star magnitude, from very bright one down to relatively dim one. And an accurate optimization of all the parameters of the system is required to get the nominal performance. And in particular, for a pyramid wavefront sensor, the number of subaperture can be changed by the detector binning. Our approach for this system is that several of the parameters, as you can see here, the gain of the MCCD, the sampling of the loop, the filter route change in function of the detected flux, so in function of the magnitude of the stars. Then the modulation amplitude is kept constant for all the conditions to 3 lambda over d plus minus 3 lambda over d. This is close to optimal, but in theory it should be changed in function of the residual. The number of corrected modes is always the maximum one, and in this case we use the ability to change the gain of each of these modes to manage this one. And finally, only the gain of the control filter are changed online. To do the optimization, to make the optimization, we start with simulation, both end-to-end and analytical one. There is some paper that show them. And as you can see here, is this all the parameter. Then we have for the real system, we have a table that, in function of the magnitude, change the binning, and so the sampling of the subaperture, the loop frequency, the gain of the MCCD, and the tip tilt modulation. During this talk, I will focus on the integrator gain, or in general on the filter gains. So in FLAO system, we have a trial and error method to regulate the gain of the system. There is 3 sets of modes which are changed. For SOL, we want to have a full modal gain optimization. We start from the work from Gendron and La, but we have a slightly different implementation. We work with pseudo-open loop modes because we have no possibility to disentangle the turbulence and the noise from the closed loop data. Then we choose to approximate the plant as a pure delay. And this modal control optimization compute the gain for filters that does not change during operation. These are the equation we use. I only would like to focus on the fact that we need some inputs. One is the plant transfer function. Then we need the filter, the roots of the filter that we use, and a range of stable gain. And this stable gain depend on the filter used and the plant we have. But I forgot to tell a thing, is that as you already know, the pyramid wavefront sensor is a nonlinear sensor, and it have a so-called optical gain that depends on the level of the achieved correction. So in theory, we have to model the plant as a delay multiplied by a coefficient. But fortunately, in the flow system, we already have a way to estimate and compensate for this optical gain. This has been done starting in 2015 for the compensation of the non-common path aberration of Lucy. And so what we can do is simply use the same algorithm that compensate the optical gain for the NCPA compensation, and so we can get back to the simple delay for the plant. What we can say about this delay is the sum of several terms. For sure the integration time, but even the readout time, the latency of the RTC, and the DM settling time. We have computed the nominal values during the design of the system, and during commissioning we have verified through test in the real system the values that we get. And another point is that this delay is not equal for all the modes, but is a modal delay because the DM settling time is different, in particular for low order modes. In particular, low order modes are slower, and you can check in this paper from Armando. Other characteristic of our implementation, this is the equation that we use to apply the gain in the RTC. You see there is some parameter, and these parameters are used to improve the robustness of this algorithm. The first thing we do is that we use a reduction of the maximum gain to get not only stability, but even a bit of phase margin, for example. Then we have another parameter that reduces the gain. This is the gain that minimize the cost function. We reduce it by a certain amount by these alpha values. And then we don't apply directly this number, but we change the gain with a limitation with the previous step. Then another thing important to say is that we coordinate this algorithm with the one that estimates the optical gain. And so they are synchronized, and we take into account the optical gain variation, the estimation of the optical gain, and we rescale the final gain by this ratio. And finally, we have a supervisor that check, for example, in this case, we check the saturation of the DM, and if the saturation reach a high level, reduce the gain estimated. So we start with daytime activity during the commissioning. We compare the old algorithm with the new one. You see there is a 3 set of gain, and we see that we can reach a higher performance. And then we go on sky. And as for the daytime result, we see that we can get a higher stir ratio. But not always the system works as expected. We start investigating why it is happen, and we see that we get, in some cases, a bistable behavior, in particular for the tip tilt. So what we see is that the tip tilt gain is not stable during the operation, but oscillates between two gain. For example, between these two. When the gain is raised, we see a huge vibration starting at 127 Hertz. And we start investigating it. We understand that this is a control structure interaction. And this limits our performance. And it happens for a huge range of frequencies, so for a huge range of magnitude. And what we see, if we check the PSD of all the modes, we see that is present on all the modes. But if we see the power is mainly on tip tilt and a bit on the second and third radial order. And another thing is that we start thinking why we see it now and not before. And what we found is that FLAO system, due to a larger delay, was not able to put energy at such high frequency. So this is the reason why only with the new system, with a smaller delay, we are able to put energy on this frequency and get the excitation. So we start thinking about a possible solution. From our side, we start working on the control. And so we decide to spend some time trying to optimize a filter that does not put energy on this frequency, but has a good rejection of the main structure vibration that we have at around 11 Hertz. And the idea is that we can put this filter in the RTC and change the gain as we do for the leaky integrators. So a few days ago, we do some daytime tests. They are successful. We are able to reduce the total jitter by a factor 3 in RMS. And we are able to go back to very good stir ratio. Take into account that here we get 70% Strel, but we have no NCPA compensated. And they amount to about 100, 150 nanometers, so they are quite large. And in the next days, we will test this on Sky with the old optimization method, but we are ready to start test with the modal gain optimization. Then a last slide. I would like to conclude with showing you a performance that we are able to get from a SOL. And we think this is an interesting result because this is a quite faint magnitude for a single conjugate adaptive octave system. And in a not so good atmospheric condition, we are able to reach high Strel on a very long, relatively long exposure. This is 80 seconds. And in another thing that for us is nice is that we are able to retrieve the performance that we estimate by end-to-end simulation. And for this particular regime, we are more than doubling the performance of FLAO system. And as you can see, even the subframes show you a very stable performance.